The following equilibrium exists in a saturated solution of potassium chloride. What is observed if a few drops of hydrochloric acid is added? So what would we be adding? We would be adding H3O plus and Cl minus. Cl minus is a common ion, so we would have the common ion effect. Too much of this product would shift the equilibrium towards the reactant, and therefore you would see KCl precipitating out of solution. The precipitation of KCl is known as the common ion effect. Define a catalyst. It is a bookwork thing. It is a substance that is involved in the mechanism of the reaction, but it is not permanently changed during the reaction, and it alters the rate of the reaction. Define dynamic equilibrium. The forward and the reverse reactions are taking place at the same rate. Methanol is manufactured by compressing carbon monoxide and hydrogen. The mixture is passed over zinc oxide, and you've got carbon monoxide, hydrogen, and you get methanol. You know your organic chemistry, so we can easily ask you these questions. What we have there is a positive rate of reaction, at least heat of reaction, and therefore it is an endothermic reaction. What is the chemical formula for zinc oxide? You can see how often this is coming up, and there is an expectation that you are able to write formulae. Zinc has a valency of 2, and you have to learn that, and remember that the Z looks a lot like a 2. So zinc oxide, oxygen is in group 6, hold hands, and it's ZnO. But it didn't have to be that, you need to work it out. What purpose does the catalyst zinc oxide serve in the reaction? It is there to speed up the rate of the reaction or to lower the activation energy of the reaction. Those would both be acceptable answers. Now it asks you to draw a neat sketch graph of the potential energy versus the reaction coordinate of this graph. So let's go. You need to be able to know how to draw this. This is considered a level 1 question, and so you need to get quite good at it. So this is labeled reaction coordinate, or it is sometimes labeled course coordinate, course of the reaction, and this is your potential energy. You don't actually need values on these curves. It's just a sketch. It's endothermic, so we're looking for a shape where the products have got more energy than the reactants. It then says, they don't ask you to label. No, not a lot of labeling. Let's go. Draw a second curve using a dotted line, so this reaction goes a bit faster. There's a lower activation energy, and it comes to exactly the same point with a catalyst. And then it says clearly indicate the heat of the reaction. The heat of the reaction is the difference between the energy of the reactants, which is here. That's the energy of the reactants. That's your energy of your products over there. And then this over here is the activated complex for the unactivated complex. And that's for the uncatalyzed reaction. That would be the activated complex for the catalyzed reaction. And if you were to ask to show me activation energy, which you're not here, that would be your activation energy. You need to be able to label these graphs. They tend to ask them very often. The reaction is allowed to reach equilibrium. What would be the effect of each of the following changes on the equilibrium concentration of the methanol? Explain each answer in terms of Le Chatelier's principle. So the first one is our increased temperature. This is an endothermic reaction. An increase in temperature always favors the endothermic. In other words, it tries to make itself cold. So it is going to favor the forward reaction, but that's not the question. The question says what happens to the concentration of the methanol, and therefore the concentration of the methanol would increase. What would happen if the pressure is decreased? Let's look at pressure. We have got 1, 2, 3 gas moles going to 1 gas mole. Remember, it's only the moles of gas that count. We want to decrease pressure, so we want to take up as much space as possible. So we will go to the 3 gas moles. When you decrease the pressure, you go to the side with the most gas moles, and therefore, if I'm favoring the reverse reaction, I am going to decrease the concentration of methanol. The next one, carbon monoxide, I'm putting more of the reactant in. That will favor the forward reaction and make more product. So what will that do to the amount of product there? It is going to increase the amount of product. Why? Because the system tries to use up the carbon monoxide that has been added. Now they give me an actual equation in terms of a Rice equation. So we're going to start by writing out the balanced equation. It's CO plus 2H2. They're all gases, so I can easily just leave them. I include them all in my Kc value. And I am going to write an expression for Kc because I know I get some marks for that. Kc is concentration of products raised to the power of the coefficient divided by concentration of reactants raised to the power of the coefficient. The only coefficient is that one over there. I am then going to use my Rice table and my ratio ICE volume, and we are going to also have an equilibrium concentration, but 1 is to 2 is to 1, 1 is to 2 is to 1 is the ratio. Initial concentration, they give me 12 moles of carbon monoxide and 8 moles of hydrogen are placed in a container with a volume of 400, so it's 0,4, 0,4, 0,4, which is then heated to a certain temperature. When equilibrium is reached, at equilibrium, there are 2,25 moles of 2,25 moles of hydrogen left in the story. So that's what's left. And calculate the value of Kc for this reaction. So the first thing I need to do is I need to draw my little link between the consumed of the reactants and the equilibrium that is left over. Those are both dots, nothing happens. I do know that if I go from 8 to 2.25, how much must I have used? Well, then I must have used 5,75. There's a 1 is to 2 is to 1 ratio over here. So this number over here is 2,875, and this number is 2,875. 12 minus 2,875 is 9,125. Now I am going to say that my equilibrium concentration is equal to that number of moles divided by the volume in each case. So I am going to just divide through each time, and I get 22,81, 5,625, 7,1875. I then substitute those numbers in for the methanol, for the carbon monoxide, and I mustn't forget to square the hydrogen. And when I do all of that, I get an answer that comes out of 0,01 as my Kc value. What does that tell me? That tells me that the reverse reaction was quite clearly favored. And then it says, what would happen to Kc if the temperature were decreased to 200 degrees centigrade? Briefly explain, if I decrease the temperature of an endothermic, I will favor the exothermic, which is the reverse reaction. So if the reverse reaction is favored, this Kc value would decrease even further since reverse is favored. And remember, a change in temperature is the only thing that can change Kc. Looking at this graph, we've got brown nitrogen dioxide. It dimerizes, which just means that it becomes 2 nitrogens and 4 oxygens to form a colorless nitrogen tetraoxide according to this reaction. We are given that delta H is less than 0, so this is an exothermic reaction. Consider the equilibrium concentrations in 3 decimeter cubed containers, and the following graph shows the amount of each gas over 30 minutes. At 5 minutes, there's temperature change. Was this an increase or a decrease? Well, at 5 minutes, I see that I get less NO2, goes down, and I get more N2O4, which means I must have somehow favored the forward reaction. How do I favor exo? I decrease temperature. Always favors the exothermic reaction. So they say, was there an increase or a decrease? A decrease. Why? Because a decrease in temperature favors the exothermic reaction, which is the forward reaction, which means that more N2O4 was made. Then it goes on to say that at 15 seconds, there's another disturbance. What's happened here? Quite obviously, I have suddenly increased the NO2. That means I have added NO2 to the reaction vessel, and therefore the system tries to compensate for that by favoring the forward reaction. What is the disturbance? An addition of NO2. And how did this affect the yield of N2O4? It increased the yield of N2O4. You see the little hump going up over there.